Good morning. I'm Bryan Cantrill. I apparently am still being haunted by Usenet comments I made over 20 years ago, so everything lasts forever. Keep that in mind. So I'm going to be presenting this morning on a subject near and dear to my heart, even though it often induces cardiac arrest, or feels that way. And that is debugging under the most stressful possible conditions. Debugging under fire, debugging when systems have failed, debugging during an outage. The genesis of this is a very, very, very bad day that we had several years ago. So this is an IRC log. I've redacted it slightly, and I've obviously changed the names, but this is an internal IRC log that shows, this is right before disaster strikes here, when one of the operators says, I'm going to reboot a bunch of empty RBs. RBs is a Richmond B. That's a type of compute node we have at Joyent. I'm just getting the list right now. Now, I should tell you now that Joyent is a public cloud company. So yes, we compete with AWS and Google and Azure and so on. So we have our own public cloud, and this is an operator of that public cloud about to reboot some of these empty nodes to bring them on to a new platform image. Another operator says, all right, sounds good, let me know when it's a go, and I'll do it towards the end of my shift, in a couple of hours. And then you see about 7 minutes later, another operator saying, US East 1 is being rebooted, question mark. To which someone replies, question mark, question mark. Like, what? That doesn't even parse. What does that even mean? Like, US East 1, that is a data center. Like, we reboot machines, not data centers. That's not a thing. And then operator 3 helpfully cuts and pastes in the message that he just saw on the head node, which is kind of the administrative node in a data center, saying that the head node is being shut down now, something that we basically never do. Log off now or risk your files being damaged. Of course, this is the classic and ancient and stupid, actually, Unix. Why do we still have this message? I don't even know. Anyway, so it just seems like it's such a vague threat that the system is making. Like, if you do not log off, I will punish you by randomly corrupting your files. Your files are actually not going to be damaged, and you actually don't even need to log off, by the way, because the system is going to take care of things by itself. So you can actually just, if you want, stay logged in and edit away, because we're going down anyway. To which one of the engineers says, so you can see, and obviously you got the timestamps here, says, WTF. One of the things that we have perhaps not helpfully done at Joyent, we have, this is our pre-Slack Slack. This is our Jabber channel here. And we've got a bot that has been, over the years, the bot has, I believe, gone past the Vingian singularity. The bot actually is, we don't actually pay the bot, but it wouldn't surprise me if the bot actually demands a salary at some point. So we've added all sorts of weird logic to the bot. One of the things that someone added along the way is anytime someone says WTF, the bot takes a random sentence from chat over its entire history in which someone has used the word fuck and offers it up. This is one example, and the bot has several behaviors where, because of course, like, the bot obviously has no mirror neurons, right? The bot actually has no empathy. The bot does not know whether this is a good time to say this or a bad time to say this, or an extremely bad time to say this. So the bot will and actually, and it has no way of gauging if someone, and this is actually, in this case, we are just stunned, not actually enraged. But another thing that the bot likes to do is correct anyone saying Linux to, you mean GNU Linux, and sign it Stallman. And Linux often comes up in a bit of a froth at Joyent. So someone will already be frothy and be like, oh, God damn Linux. It's like, you mean GNU? It's like, shut up, bot. Shut up, bot. Someone delete the bot. I'm deleting the bot. I'm deleting the bot right now. I've had it with the bot. So anyway, the bot has no sense of timing. engineer says WTF, like, oh, the case that blows this fucker up is pushing up large files. Like, yeah, ha ha ha, bot, shut up. Another operator is like, what? And of course, the first engineer says, which I mean, I just love the fact he typed out what everybody is thinking during any outage. Please don't be me, please don't be me, please don't be me. Which is, I think, speaking personally, if I'm traveling through life, nobody is more tolerant of a systems failure than I am. If I go to check in for my flight, I'm like, oh, I'm sorry, sir, we're having computer problems. I'm just like, oh, that's fine, take your time, please don't be me, please don't be me, please don't be me, please don't be me, please don't be me. Please don't be me, please don't be me, please don't be me, please God, don't be me. And this is not the engineer who's saying, please don't be me. It's the first operator. And actually, so I think that there are a couple of kind of key things to point out to this. One is actually, this is pretty amazing candor, because this guy realizes that he just accidentally nuked the data center. And there was no attempt to, I mean, this is basically the shortest possible way he could express that, right? There's no attempt to, like, there's no flowery language here, no, like, deliberate ambiguity. It's just like, it is me. I am become death, the destroyer of data centers. To which engineer one, who has the kind of residual paranoia that exists in many, if not most engineers, asks the reasonable question, deliberate or not. All right, like, is this an act of sabotage? Are you, I don't know. And he says, accident, I was rebooting Richmond B, okay, phew, and forgot to put -n, we'll talk about that in a little bit. I fucked up, I'm sorry. I truly, truly sorry. Just like, we are all, yes, sorry, yes, yes. We are, and at this point, like, you're not even upset. You're terrified. I'm terrified. Operator 5 wants, I don't know why, I think Operator 5, I guess, just wants to hear it directly. Like, so you just got the head node, or you got all of East 1? And he's like, so I did this, and I actually redacted it because it's got a bunch of UIDs and machines, but here's what I did. And at this point, the support personnel have realized, like, wait a minute, something very bad is going on. So the support personnel come into the chat like, so all of East is going to reboot? And engineer 2 says, yeah, you just rebooted all of US East 1. Yikes. So, I have never had a more visceral thought that I was going to throw up on my keyboard, because I knew that this was very bad, very, very, very bad, and that we were going into total unknown land for a lot of reasons. I'll get to the reasons that this is total unknown land here in a second, but this was absolutely terrifying. This is not just like we're going to reboot the machine. I know that we are, but just to show you, yeah, exactly. So this is, thank you, the register has the mushroom cloud. And so first of all, just before we talk about kind of the details of why this was so terrifying, just almost instantly, and actually I think we rebooted it at what? We reboot at, this actually happens at what, about 2014? So we're at 2019, only 5 minutes into this. And one of the operators, I think, says, hey, we're gonna need a postmortem on this, of course. We obviously need a postmortem. But I think this was kind of interesting. I've almost done exactly what he did a number of times. And then I think this is kind of interesting in terms of like the emotional aspects of dealing with one of these outages is, let's work on recovery and just, help us out. And I have to say, through the whole outage, the operator that did this was just as helpful as he could possibly be. He or she could possibly be, I guess. They were as helpful as they could be. I think that's kind of an interesting, like, look, just help us out. I also think that it's not saying that, hey, it doesn't matter, or it'll be fine, because it's like, no, it won't be fine. It does matter. It's bad. But don't worry about it. Like, just help us recover. Help us recover. I do love, like, I'm not seeing any alerts. Like, why am I not seeing any alerts? I'm like, yeah, those are all dependent on US East 1 being up. So that's why you're not going to see anything out of this system, because this system has now gone totally 100% dark. And of course, the tweets start coming in by, 8 minutes into this, the tweets are coming in. And so why were we lucky? Well, or how could this have been so bad? Why was I so terrified? Why was I going to throw up on my keyboard? I was going to throw up on my keyboard because this is a cloud. And the software that we have built for this, called Triton, it's open source software, it's a complicated distributed system. And in particular, when the way we are able to expand a cloud and build a cloud out quickly is when we rack, stack, and cable a bunch of compute nodes, we don't actually install the operating system onto any of those nodes. They just pixie boot off of a head node. They get a platform image that they run RAM resident, and they run, which is great. And it's a huge win in many, many, many dimensions. And then there's this dimension. Because in order to know even which platform to boot a compute node, that the head node should boot a compute node, it talks to a distributed system to figure out, okay, what compute node are you, what platform image are you running, and so on. And it's going to talk to a database, it's going to do a bunch of things. There are a bunch of components required to figure out what you should boot. And of course, the thing that we are about to find out is how many of those components are sitting on machines that we can't boot because they themselves aren't up. And now, we had considered this, for sure. We had considered it, we had tested it, but at nowhere near this scale. And the second this happened, actually, well, the second I actually had an honest-to-God fight-or-flight reaction, where I actually couldn't think for about 10 seconds because my brain just kind of went white. But as I realized that this could be a very serious issue, I actually thought back to a presentation I had seen by Mark Imbriaco, who is here, and was at, I believe it was on a Heroku outage, a very, very, very bad day at Heroku, and an outage that lasted way more than 8 hours, if I remember correctly. Was that? 67 hours. And I absolutely thought, like, there is a, 40% chance we're in a 67, we are in minute 1 of a 67-hour outage. And I immediately planned for a 67-hour outage, mentally. And in a lot of ways. One, I took a subset of engineers and I asked them to assume that we can't boot any of these and go figure out how we boot a compute node with an image that we are going to handcraft and hand roll and boot. Let's just assume that this is not going to work. I also began to immediately plan. Fortunately, this happened in bullseye working hours in California. But one of the very interesting points that Mark had during that outage was planning for sleep management. Because sleep deprivation is a major judgment impairer. And one of the funny things about judgment impairment, and this seems to be true however your judgment is impaired, the very first judgment to go when your judgment is impaired, from sleep deprivation, from drinking alcohol, from anything, the very first judgment to go is that meta judgment that your judgment is impaired. I guess it's the way judgment impairment works. I guess it's a little kind of a little twinkle in the eye of judgment impairment. It's I like to roll this way. I like to mess with the world like this. Because you are convinced that you're fine. It's no, your judgment is actually impaired. And you actually, and in particular, there are, and we've seen them recently, there are many incidents that happen at the end of a shift or when people are already tired, and then they stay up for another 12 hours when it's you should be in bed. You should be asleep, or someone else should be working on this problem. So my mind was already going to all sorts of crazy places. And fortunately, the whole thing came up. And because the things that we actually had designed, it actually worked. Everything actually worked the way it was supposed to work, which never happened. So no one was more shocked than I was. And in particular, it was, and I should have cut and pasted the chat because it's pretty funny about among other things, Joyent.com is offline, right? I mean, everything's, US East 1 is gone, Joyent.com is gone. So we are in the process of failing the website over to another data center just so we can tell people, yes, we know we're on fire, sorry. So we are in the process of failing that over. And then that is successfully failed over. It's okay, thank God I go to the website. And the engineers are like, well, that's funny because we haven't actually failed it over. I'm like, wait a minute. If you haven't failed it over and I can go to the website, it's like, we're gonna live! We're gonna live! We're gonna live! Oh, thank God, we're gonna live. And so essentially the entire DC, due to some mechanisms that we had added to the system a long time ago, precautionary mechanisms, in the event of a cascading failure effectively, the system came back up, thank God. And we lived. And it wasn't that bad. I mean, people were down. I mean, it was bad in that everyone was down, and it was a news story, and so on. But this could have been so much worse. This could have been so much worse. And it was, I wouldn't say it was a wake-up call, because we always know that things can be bad. But it was, for me, it was certainly the most stress I have had during an outage, where you have that honest-to-God feeling that, I might not get out of this. We might never actually recover. I might go full Magnolia on the cloud, if you remember those folks, who had an outage from which they did not recover. And that was, they had I believe it was, which they named the technology in case I get it wrong, but I believe they had a database failure from which they couldn't recover. So, wow, how did we get here? How did we, a bunch of software engineers, end up with such a high stress activity? And the nature of software has changed over the last N years, and software is increasingly being delivered as part of a service. I mean, that is the vector by which we deliver software, and it's increasingly automated. It's the way we deal with all the software, the way we configure it, the way we deploy it, the way we manage it, it's all automated, and that's great, right? But that power of the automation is part of what cut against us in our outage. If that outage had been 10 years prior, it would have been like, okay, we're bouncing all the machines, but it's not a big deal because these machines have all have their own operating system, they're all gonna boot. It's the fact that we had a much more sophisticated automated system that made that so perilous. And our automation is not complete. We are not actually post-singularity, despite what the bot will tell you in chat. Humans are still in the loop. Even if they're only developing software, humans are still in the loop. And I'm here to tell you, semi-automated systems, and they are all semi-automated. These are not fully automated systems. Semi-automated systems are fraught with peril. History tells us this over and over and over again. It is the curse of the intermediate skier, if you will. If you ski as an intermediate, you are most likely to kill yourself running into a tree, because you now have the confidence to go faster, but not the ability. And semi-automated systems give us the confidence to do incredible things, but with humans still stuck in the loop in ways we understand and ways that we don't understand. And with that human fallibility in a system that is more manual is actually safer. A human fallibility in a semi-automated system is actually much more dangerous. And look, it wouldn't be me if we were not going to talk about historical accidents, right? So clearly, there are going to be some historical accidents in here. And does anyone recognize this? If you're Canadian, you're probably Canadian, because this is it tells you all you need to know. Are you Canadian? Yes. He nods yeah. I know you're. It's okay. Welcome, Canadian. It tells you all you need to know. I love Canada. I spent a lot of time in Canada. It tells you all you need to know about Canada, that this is a source of national pride for Canada. You are looking at a source of national pride. How could that possibly be the case? This is what's known as the Gimli glider. So this is an aircraft, this is a 767-200 that had an impossible failure. It ran out of fuel at 30,000 feet. And the reason it ran out of fuel at 30,000 feet is because of human fallibility. And in particular, the airport in Montreal was cutting over from imperial units to metric units, miscalculated something in kilograms, or entered something in kilograms that should have been in pounds, and this had much less fuel on board than they thought. And the fuel gauges, by the way, I mean, this is like interesting to know about the 767-200. It is the amount of fuel that you tell it that it has when you take off. It's like, okay, that's how much fuel I have. And so that's the size of the gas tank. So they're like 30,000 feet. They're like, oh, no, you have plenty of gas. And you're like, oh, you just lost one engine. They're like, oh, God, okay. They're like, oh, you've lost the other engine. You're like, oh, my God. And never, ever conceived of by the 767-200, this is 1983, this is one of the first glass cockpits. There are no cables in this aircraft. If you know an old pilot, they'll tell you that the 707 was the greatest aircraft ever built because it was the last one that had cables. This is all hydraulics, all glass. Cockpit goes dark. They lose it all. They have lost their auxiliary power units. They've lost all power. The only power that they are actually able to have for this aircraft, something called a ram turbine, that they I mean, it's like, talk about like your power generator of truly last resort. It is a propeller that drops out of the plane and uses the airspeed to provide power to the aircraft. You're definitely not supposed to fly on this thing. And by the way, one of the interesting aspects of this accident is as they slowed down to glide this thing into a landing, and by the way, glide, it's a 767, it does not glide. This is not a glider, this is a brick. Aerodynamically, this thing is a brick, and it was falling out of the sky. As they were losing airspeed, they were actually beginning to lose power in the aircraft as they were landing this thing. This lands on an old runway that had been turned into a drag strip and then a flea market. So can you imagine being at a flea market in Winnipeg as a silent 767 falls towards you? And when you think of that, if you're Canadian, you are now singing "O Canada" in your head because it was an amazing act of airmanship that they landed the aircraft. And they put put other pilots and simulators in this, and they all crashed and died. I mean, it was very unusual for pilots to be able to land this. This was a scenario that they had never trained for, they had never seen, the engineers had never, and this is their equivalent of rebooting the data center. It's like, didn't really think that one was possible, actually. It turns out it is. It is. So, and this again is the peril of that semi-automation. You've got the glass cockpit, but still the human fallibility. Closer to home, right? The S3 outage probably affected many people in this room. The S3 outage from just a couple months ago, right? From February. If you read this postmortem, they actually bounced the wrong boxes, effectively. It was effectively, it was a human in the loop that specified the wrong machines. The key is, we're always going to have a human in the loop. Don't think you're going to get the human out of the loop. We will always have a human in the loop because there's a human writing software at one end of it. So we're always going to have a human in the loop. We're always going to have a peril of semi-automated systems. How do we manage that? How do we make them as reliable, as robust, as debuggable as they can? And how do microservices, I guess this is like, this year at GOTO is like the adieu to microservices, given that the track is being blown up next year. So I'll send microservices out by reflecting on the complexity they add to a system. Because the paradox of microservices is we are attracted to them for their simplicity. A developer, and many of us are developers, are like, oh, wow, I get to like reason about a much smaller problem, which is true and great, but they yield a more complicated system. And which is not to say that microservices are wrong or misguided. They certainly can be if taken to an extreme. But it's more that we need to be cognizant of that. We need to understand you're building a distributed system, and when don't add a microservice to a system because you don't want to work with another organization, which, by the way, I am convinced is like 40% or more of the microservices boom is inter-organizational strife. Where it's like, well, screw those guys, we'll build our own thing. It's a microservice, yeah! You know, with microservices, no one has to be in charge. And I think that some organizations have taken this to do whatever the hell they want, whenever they want, but then they are yielding a much more complicated system. Open source has also exacerbated this. I mean, obviously I love open source, it's critical, but it allows for many more kinds of choices. It has increased complexity yet again. The abstractions themselves are becoming more robust. They are robust. But as the abstractions become more robust, failures become rare. That's great. But the failures become worse. And again, this is that curse of that intermediate skier. As the abstractions become more robust, we are tempted to believe that the systems are infallible. And yet, they are not infallible. In fact, they are most dangerous in that we are thinking of them as infallible. And the fact that we've got a distributed system here, and these failures, when this whole system fails, you are likely going to have failures in disjoint subcomponents, disjoint services, disjoint microservices. One failure in one microservice inducing a failure in another, inducing a failure in another, getting true cascading failure. And so this has been, obviously this was a tweet from a couple of years ago that got retweeted a bunch. We replaced our monolith with microservices so that every outage could be more like a murder mystery. Now, which obviously I think is funny. I think I probably liked it or retweeted it myself. But like, look, anyone who's been in an outage knows that an outage does not feel like a murder mystery. It doesn't feel like Miss Marple sleuthing around in a quaint English town to see who done it. That is not what an outage feels like. This is production. Production is war. War is hell. An outage in production does not feel like a murder mystery. I mean, that's what it feels like to me, right? And especially as a big and complicated system begins to fail, it's often chaos. Alerts firing everywhere. Alerts that are some misguided, some confusing. Everyone trying to figure out what's going on. Total chaos. Every engineer saying to themselves, please don't be me, please don't be me, please don't be me. That is, to me, is what microservices more feel like. And the modern software failure mode looks more like this. Anyone recognize what this is? This is the blackout from 1965, Great Northeast Blackout. Tripped, and this is power systems. Boy, power systems are complicated. So there was effectively a breaker in Quebec or upstate New York, I can't remember, that was not, that was set at a level that was kind of a dated level. They didn't realize that actually normal loads could go that high. It's November. There's a lot of lighting, a lot of heating. People are drawing a lot of power. And this particular intertie actually shorts out. It hits its breaker. It turns itself off. One of the challenges of power distribution systems is the power's got to go somewhere else. By the way, microservices have the same problem. Your microservice decides that it turns off. That load goes somewhere else. And all of that load now goes on. And if you are going dark because of load, you have now gone dark at the worst possible time. And now those other interties are much more likely to themselves go dark and generate yet more load for the rest of the system. So this is this fallacy of like, oh, well, I've got 100 of these. It doesn't matter if one of them dies. It's like, well, it depends on why that one died. Maybe not, but you should understand why it died. Because if it died because it was overloaded, that might be the true canary indicating that there's actually a much more serious problem, and you've generated more load, and you've got this potential runaway failure where you actually have total systemic failure. And in that regard, I feel that this is actually the most apt metaphor for modern software deployments, systems and software deployments. Do anyone know what this is? 3 Mile Island. I think I heard someone say this is one of the very few photos taken inside the control room during the incident at 3 Mile Island. And here is the 3 Mile Island microservices architecture. So I'm just going to give you some quick education on 3 Mile Island because you're going to see a lot of parallels. So if we look kind of over here to the right, you see that demineralizer and that condensate pump. This all started because of some routine maintenance where they were running auto vacuum on a Postgres shard. No, excuse me, I'm sorry. They were cleaning out the demineralizer. The demineralizer, they use resins to demineralize it, and these resins can kind of glob together and get stuck. They can't clear this thing out, so they decide to put some air in there, to shoot some air in there to kind of get these resins unstuck. That air ends up getting into one of the control lines for that condensate pump. That condensate pump goes offline, which is actually okay. I mean, not okay, but it's fine. There are auxiliary pumps that are actually supposed to start pumping water at that moment to cool the reactor. All 3 of the auxiliary pumps had their valves closed because all 3 were offline for maintenance. It's like they had not checked the database backups. Yes, they had not checked the database backups, right? It's something that we've seen as recently as the GitLab outage, where this is a very common failure mode. When you have auxiliary systems, when you have backup systems, those systems are often not checked. And when they fail, they often fail silently, or they fail, it's like, oh yeah, we know the auxiliary pump is offline, but that's fine because it's an auxiliary pump. Well, it's like that one microservice that crashes. It's like, it's fine, but you've begun to compromise your reliability. With all 3 offline, and one of the major findings of this is that the reactor should have been taken offline if all 3 were offline. With all 3 of those things offline, the reactor begins to heat up. Again, not the end of the world, but you know, this is getting a little bit exciting. And that number 7 towards the top of the containment building, what's called the pilot operated relief valve, that opens up to let out all the heat from the reactor, and the reactor scrams. Control rods go in, and the reactor stops, ideally. But still has a lot of heat. Okay, so far so good. The pilot operated relief valve then, and this is we get to the actual, I think this is the analog for the way that we think about services. The pilot operated relief valve closes when the temperature gets low enough. Well, the temperature begins to get relatively low, but the pilot operated relief valve does not close. Of note, the light that sits on the control panel indicating that the pilot operated relief valve is open goes dark. This was a UI disaster. That light goes dark not when the relief valve closes, which is what the operators believed. That light goes dark when power has been applied to the solenoid to close the relief valve. I told the relief valve to close, not the relief valve is closed. The operators were being lied to. And they had other ways of figuring out what was going on, but they didn't. For reasons that are actually very understandable. And in the final findings of this, the operators were actually held blameless because this was such a difficult condition to figure out. That the reactor, if you knew that the relief valve was actually stuck open, then everything made sense. And you were actually losing all of this steam, all of this coolant out. And notably, you see there's that drain tank down there and that rupture disk. All of this coolant goes into that drain tank. That drain tank overflows, the rupture disk breaks, and there's water all over the bottom of the containment unit. Alerts going off about that. All those alerts are being ignored because there's so many other alerts going off. And this is the whole idea of like, oh, we monitor everything. Like, we alert everything. This would, monitor everything, alert on everything. Okay, sure, but don't think that your alerts and your monitoring are a substitute for understanding the way the system works. Sometimes we have this church of alerting and monitoring. And we believe that simply by monitoring it, simply by alerting upon it, we have averted disaster. That's exactly what the nuclear industry thought in the late 70s. The nuclear industry, by the way, the nuclear industry was destroyed by 3 Mile Island and never recovered, even though the incident was actually not that serious. We've had many incidents in other domains that are much more serious. This incident was not that serious, but it did destroy nuclear power for a lot of reasons. And I love this finding from the special report because, boy, does this feel current for us. It's a difficult thing to look at a winking light on a board or hear a beeping alarm, let alone several of them, and immediately draw any sort of rational picture of something happening. And the more alarms and alerts you have, the more you are creating sensory overload for the operator, and the more likely it is that the operator will be looking at an alert or a monitoring alarm that is symptom more than cause. This is not to say that you shouldn't monitor. Obviously, you should. We should monitor our systems. We should alert on them. Just don't fool yourself, don't delude yourself into thinking that we have avoided an outage as a result. So we suffer from many of these same problems. We suffer from the arrogance of nuclear power in the 70s. We are gleefully deploying these distributed systems with this erroneous idea that they somehow can't fail, that they're infallible because they're running on more than one computer. It's like it turns out there are things that can affect more than one computer. Trust me, I know. It is me, as they say. So what does it mean? So how do we actually debug these things when we fail? Well, one of the things we have to wrap our brains around is that we will need to debug them in production. You will need, as a software developer, and I know if you're a software developer, you're just like, can this problem please just go away? Can I just go, please? Can I just go back to my little, I know, no, this problem can't go away. We need to actually debug this software in production. And that prompts actually a deeper question. How do we actually debug? So in the abstract, debugging is the process by which we understand the system. And I think that this is a very kind of important difference in the way we view debugging versus the way it's been viewed traditionally. Debugging is not merely the act of making bugs go away. It is the act of understanding, gaining knowledge, new knowledge about the way the system works. That's what debugging is. And the behavior that we're understanding is particular pathological behavior that we want to avoid. Now, this whole idea of like understanding behavior in a system, yeah, we've done that before. That's called science. Science. We have the natural world. We want to understand it. We want to reason about it. That's science. Now, the natural world is a real pain in the ass. We've got it, like, never complain about being a software engineer, please. Because we have it so incredibly easy. Things are so cheap and malleable for us versus in the real world. The real world is such a pain in the ass, where you have to do big, expensive experiments. And you can't just like go into an experiment not having no idea of what you're trying to do. You've got to be, almost by definition, very hypothesis-centric. You have to have a hunch that you're checking out. And that hunch probably needs to be right. And then you need to design your experiment to invalidate that hunch. It's hard, it's expensive. We have got an incredible luxury. Software is entirely synthetic. We live in this unbelievably, these luxurious systems of synthetic mathematical machine, and the conclusions that we draw are often not likely true, but provably true, which is a tremendous luxury. And we can perform experiments so easily. They're so cheap to perform experiments. And even more importantly, when we have questions of our systems, we can simply ask it. We wrote all the software. We did actually write all this. I know sometimes it doesn't feel like that, but we actually wrote all of this. Like, we can reason about this. This is not a system that has been evolving for 4 billion years. This is a system that is, every line of code you're looking at is less than, 60 years old. And most of them are a lot younger than that. We can understand it. And we can understand software simply by observing it. And I think that this is one of the key things to realize about debugging. The art of debugging, because I think when you're around someone who understands how to debug very well, you might not understand what they're doing. And by the way, they're kind of doing that intentionally. There's a little bit of leisure domain on the act of someone who can debug very well, in that it's very easy to, they kind of disappear for a while, then voila, I present the fix. It's like, how did you figure that out? It's like, oh, a debugger never tells. Oh, what's that? You have a coin behind your ear. Oh, okay, there we go, Jimmy. Would you like a balloon? So we kind of like to kind of present this idea that we're like magicians. We are not magicians. We are the Wizard of Oz sweating behind a curtain, frenetically turning a crank, trying to figure out the problem. And those that can debug well know this. Those that debug poorly don't know this because they debug poorly and they suffer from poor self-awareness. Debugging is the act of asking questions and answering them, not guessing what the answer is. You are playing 20 questions. And when I say 20 questions, I mean not 20 questions with my children who are unbelievably annoying to play 20 questions with. So they'll be like, okay, 20 questions to play. All right. Okay, Dad, is it a badger? I'm like, no. Like, how about like, is it a mammal, or is it an animal, or is it a vegetable? It's like, yeah, but is it a badger? I'm like, no, don't you understand? It's like, Dad, is it a badger? And you're like, fuck, it is a badger, but damn it. It's like, they're not. It's like, I will confess, I have changed my answer to 20 questions just to like teach them the larger lesson of like asking better questions. You want to form questions, not hypotheses. Because too often, what people do is oh, I know what it is. I know this. It's over there. Oh, I fixed it. It's in. It's pushed. It's like, whoa, 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 whoa. Whoa, how did we go from you guessing what it was, having a fix, pushing it, oh, we didn't see it again. Well, we didn't see it again. That's not actually, that doesn't actually prove your hypothesis correct. We should be asking questions. And as those questions give answers, those answers are facts. And those facts constrain hypotheses. And we repeat this process of answers to questions, making more specific questions, more specific answers, more specific questions, more specific answers. And then that hypothetical leap is often not a leap at all. It's a step across a puddle. And I've debugged a lot of nasty bugs in my life. That has always been the process. And there have been many, 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 many bugs where even as I was nanometers away from the final cause, the root cause, I still couldn't believe it. And it was only when you actually get to that final answer, like, oh my God, this is a microprocessor bug, or what have you. So that is the way we debug. We debug by having the cycle of questions and answers. And this takes many forms. It means that, how do we ask questions of software? And in particular, those of us that are software developers, how do we design our software to answer questions about itself? That, if the art of debugging is asking questions, the craft of writing debuggable software is designing your software for someone else to be able to ask questions of it. It means designing for postmortem debuggability. When this thing dies, I generate a core dump. Have I left the breadcrumbs around my address space to make it easy to figure out, or easier to figure out, what happened? It's designing for in-situ instrumentation, the ability to instrument something while it's running. It's thinking about, like, how would someone want to instrument this, and leveraging things like dtrace and so on. It's designing for post hoc debugging. Post hoc debugging, totally after the fact. Logging. Logging is very, very helpful, right? And obviously logging, there's a parallel to logging as well, but logging and knowing what to log and when to log, that's the craft of writing debuggable software. And it's essential to avoid debugging in production, because you really don't want to debug during an outage. Part of doing that is creating a culture of debugging. Again, when we view debugging as understanding the system, improving the system, not merely as the process by which problems are made to go away, we can enshrine debugging. We can think of this as a first-class operation, and we can encourage ourselves to actually root cause things. If an engineer smells smoke, they should root cause that. Is that a fire in the kitchen? Is that the coffee maker? Or is that the fire raging in a coal seam, which I've discovered way too many times in my career? How could this ever work? You ever said that to yourself? Oh my God, how does anything work? Turns out it's all by accident. It's like, oh my God. How does this ever work? The reason you got there is because there was an anomaly, a phenomenon out here that you were able to complete root cause. But we must have an organizational culture that encourages that. That must not be perceived as like, oh, that's your 20% project. It's like, I want to punch you in the face. That is not like a free time activity. That is a core part of the software we are delivering. And we've got to take the extra time to build for debuggability. This is part of a very radical, controversial idea I'm calling do it right the first time. I know. It's like, do it right the first time. Oh, never. No, we don't even do it right the 15th time. It's like, try doing it right the first time. Rewrites are very, very expensive. And the cost of the rewrite is never borne by the technical debt that induced it. By the way, those people are often off to other jobs, just to put it bluntly. And if you're wondering why, when I look at a resume and I see 18 months, 18 months, 18 months, 18 months, 18 months, I want some pretty good answers. There can be good answers. There can be lots of good answers. Startup failed, crooked founder, crooked. Okay, well, all right, okay, I've been there, all right, fine, yeah, fine. But what also happens is that people actually make a bunch of bad decisions and move on to the next job. And those that bear the cost of those decisions are left silently screaming in their wake. So we have to have a culture that encourages us to do things correctly the first time. So how do we do it during an outage? Well, during an outage, everyone is going to discover whether they are who they actually are. When we say DevOps, everyone's like, oh, DevOps, hug ops, like let's get together. That's great. I'm all about like hug ops. But at the end of the day, I'm sorry, you are a developer or you're an operator. We can get very close together. We can have very tight empathy for one another, and we should. But this is the moment that you'll know what you are. The moment you've got a service, the service is up but impaired. You know that restarting the service will restore service to your customers, but it will lose information such that you cannot debug it. If an inner operator will be like, look, gotta restart it. An inner developer would be like, look, gotta debug it. It's like, gotta restart it, really need to debug it. Okay, so you need to not get trapped into a false dichotomy. You need to both restart it and debug it. And find the ways. How do we resume service without losing information? What degree of service can we resume with minimal loss of information? We do not want to overemphasize recovery with respect to understanding the way the system works. We don't want to so believe in recovery that we actually no longer understand the system, and that we believe that broken software can simply be made up for things by restarting everything all of the time. It's like, that's called Windows, and humanity did that experiment, and it didn't work, okay? So we actually need to understand the way these systems work. If we enshrine recovery in lieu of actually understanding broken software, we normalize broken software. Software should not be broken. Uniquely among the things we make, software should not be broken. It's a mathematical machine, for Christ's sake. It does not wear out. Get it right, please. We uniquely can get it right. And if you ingrain this idea that software is always broken, there are all sorts of bad things that come from this. The idea that software should tolerate bad input. No, it shouldn't. Software should fail explicitly. If you want to troll certainly any Joyent engineer into not being productive for the rest of the day, say, hey, did you know that I can do npm isInstall instead of install and it will actually work? And just be like, psst. This is when like the bot is cheerfully offering things and anyway. Software should recover from fatal failures. No, it shouldn't. If you have an uncaught exception, it is your duty to humanity to die. Generate all of your state. Present your embalmed carcass to Quincy ME. I cannot make a Quincy ME reference. I'm sorry. You have no idea what Quincy ME is. Not your fault. Those of you who are millennials, not your fault. Not a very good show. So we can actually go debug it. We don't want to catch our SIG-SEG V handler. That is bullshit for a sophomore computer science project. That's not the way we should actually develop software. The idea that like software should not assert the correctness of its state because it keeps dying. As recently as Linux, right? Linux getting rid of bug on because it's causing too many crashes. It's like, these assertion failures are compromising our reliability. It's like, okay, do you really want me to connect the dots for you? It's like, so we're getting rid of them. You're just like, oh God, oh Linux, you enrage me. You mean GNU Linux, shut up, bot! Anyway, all of these anti-patterns impede debuggability. And I promise I'm wrapping up here. In terms of after an outage, we need truly complete understanding. And yes, postmortem. I mean, of course, you want to write a postmortem. But that postmortem, it's so much more important that you completely understand what happened than it is that you write it up so it forces you to completely understand it. That's why you write it up. the write-up is to force complete understanding. We need to complete understand them, and it's very hard, especially with cascading failure, to actually unwind everything that went wrong. And you've got to ask yourself, why did these two things fail? They were up, but they were giving errors. Let's figure out why. And you often will, again, discover yet more coal fires, yet more things that work by accident. And you've got to encourage software engineers to understand their own failures, to encourage them to design for debuggability. That gets us to true software robustness. We need to differentiate operational failure, something that went wrong in the system at large, versus programmatic failure. For programmatic failure, you need to actually die. Operational failure needs to actually be handled. So, look, it's always going to be stressful. You're always going to want to throw up on your keyboard when a service is down. This is not going to, I'm not here to make this easy. It's not easy. And when a service is down, we've got some tough choices to make. I think plan for a long outage. Plan to gather as much information as you can to debug it. Be careful when you step. Missteps are really, really costly. Often a failure that I see in outages is that they are exacerbated by an early misstep. Look at the GitLab outage. The wrong database was deleted in the GitLab outage. Why was the wrong database deleted? Because they were having another problem. They were already in another problem that was, relatively speaking, a more minor problem, and the famous operator 1 deleted the wrong database. That was an action. They're doing that because they want to get the system back up. Yes, you want to get the system back up, but please stop and think. Please. It's worthwhile to say, okay, everybody away from the keyboard, can we have a con call, please? Let's have a con call, and let's get some ideas out there. What are some questions that we can go ask? If in 3 Mile Island they had done that, everybody away from the console for a second. Let's take a second and really think. They would have actually figured out that the pilot operator relief valve was open. Indeed, it was the shift change that figured it out. Because fresh minds came in and like, wait a minute, this is what's going on. Paralyzed by having different teams take different avenues of investigation and view these outages as an opportunity. They allow us to understand our software and, more importantly, develop a culture around software that values debuggability. Now, if somehow you have not reached your LD50 of me, and I take no offense if you're just like, if I'm giving you your own fight or flight reaction, but if you haven't and you love debugging, there are definitely lots of places that do this, but you should come work for Joyent. If you love debugging, Joyent is hiring. Actually, Joyent is hiring even if you don't love debugging, but if you love debugging and you value debuggability, this is something that we value very, very much. And I hope that you find an organization wherever you are that values it. And if you haven't had enough of me, but you could deal with a little more of me, but not too much more, then we've got a session up there with Bridget. And with that, thank you very much.